Okay. Let's see. Hello. So I'm not happy with the progress. How slow I've been on these changes to Ember. Uh, the main feature, yeah, was graphing data. That's the main feature we were working on. I need to update that branch. But I printed off root mean square layer normalization. Um, because I had just been reading about RMS prop, which is an optimization technique. But root mean square is basically the same technique but applied on a per layer basis. It's actually built into the layer rather than the optimizer. So I thought that would be, and there are many techniques like it that can either be normalization. Pretty much every normalization I've read about can either be implemented in the backprop algorithm or in the layer itself. And I feel like implementing in the layer itself is more similar to the way it would occur in biology. And the results between the optimizers and the layers are usually comparable. So I feel like implementing a greater variety of layers with different normalization strategies might be a better general approach, um, because then you can still use just regular backprop, which ends up evaluating the same calculations just within the layer. Uh, but um, some people, some papers have shown the use of both regularizing or normalizing layers with normalizing optimizers, and they say that the effects cancel or can even become unpredictable or unstable. So it's worth implementing in both so that both can be used independently or for test purposes together. Um, but before I get to implementing this, I should really finish the statistics objects and data collection so I can start finish this feature graphing. Ooh, sorry. Feature graphing. Mm, or data graphing feature. So, and I do want to rework the UI so that so that we can actually build models instead of hard coding them. Obviously, I need to figure out why fucking Android Studio. Why it won't run from the gutter anymore. What is wrong with my environment that compose doesn't work anymore from the gutter? It only works from the command line now. And that happened during the Android Studio update. So, and I did already try updating. I did already try installing the latest, but that was broken in a different way. Hopefully, let's check for updates to see if there's a patch 3 yet. Oh, Narwhal. Oh, 2025 1.1. Oh, nice. Okay, so I think I'm on Meerkat. Yeah, I'm on Meerkat. Okay, fantastic. So Narwhal's out. Okay, that's worth updating just to see if I can actually run my programs again. Oh, but while I'm updating, let's just do an assessment of the program and put together a list of improvements. Let's see. I don't need to update Dart. Don't need to update Flutter. Yeah. Oh man. I hope SQL Delight's fixed. What a disappointment when that broke. Oh gosh, yeah. That's what I totally forgot. That's what killed my momentum on XYZ. Is I kept every time I tried to automatically deploy, it would the build breaks every single time on GitHub because for some reason SQLite is not generating the interfaces on GitHub, but on GitHub only. It works locally. I've checked the JVM version, I've checked the Gradle version, I've checked Gradle caching, I've checked the build cache, project build cache. Cannot figure out why SQLite is not generating interfaces. But that's fairly minor. It's okay. XYZ, we'll check on that. XYZ. XYZ build process status. So we'll just check if we can submit a build to be run on GitHub and do a little problem solving. But not much because that's been a persistent issue with no explanation. And of course I can always, I mean, it's nice to be able to run tests on the server, but I can always run tests and build locally for release, which is not a professional standard, but it works. Let's get rid of some notes. Got Shannon entropy, basic definition, and I don't need this, I recognize this. Let me see if I can. Okay. So the entropy of a particular signal of a particular probability is the negative log base 2 of the probability. Yep. Okay, and then the total entropy of a system is the negative sum over all probabilities of the log base 2 of the individual probability. Oh, that's right. Okay. Oh, shit. That's right. And it's the weighted sum. So it's the probability times the log base 2 of the probability. Okay, I forgot to multiply the probability. Okay, so the partial entropy, or the entropy required for a particular probability, is minus log base 2 of the probability. The total entropy of the system is the negative sum over all probabilities of the probability times log base 2 of the probability. Okay. Oh yeah, and then the sigmoid, or no, not the sigmoid, the logistic curve, because sigmoid can refer to any S-curve function, like tan H. But the logistic curve is 1 over 1 plus e to the minus x. Yes. Yeah, and the domain is negative infinity to infinity, and the range is 0 to 1. Open set. Okay, and then, oh god, tan H. It's a bunch of exponentials that simplifies. Let's see, what is it? It's normally e to the x plus e to the minus x all over e to the x minus e to the minus x, which simplifies to, no, that's not quite right. Crap, how does it go? Oh no, I did have it right. E to the x plus e to the minus x all over e to the x minus e to the minus x. Right, which then if we multiply by the ratio of 1 represented by e to the x over e to the x, effectively multiply by 1, then we can simplify to e to the 2x plus 1 all over e to the 2x minus 1, which simplifies the computation because we only have to compute e to the 2x once. And then we just have an addition, a subtraction, and a division. It's much easier than four exponentials or two exponentials. Which, ooh, I think I forgot. I think I actually implemented tan h. Okay, no, I'm just using the math library. That's annoying that it always goes through double. I guess it's greater precision. Whatever. Okay. Oh yeah, and then the domain is negative infinity to infinity, and then the range -1 to 1 open set. A swish. Oh, that's why it's swish is that newer one. But that's using it. They call it. They say it uses sigmoid, but it specifically uses the logistic because if you use tan h, it works differently. Instead of forming a minima or maxima to the left or the right of um, the origin, tan h, when you implement swish with tan h for the sigmoid, and it creates an upward or downward, basically parabola. So it makes it between absolute value and parabola. So whereas swish with logistic looks like relu mixed with or it's a soft transition between relu and then also negative relu, which also has an important characteristic to avoid vanishing gradients. Is that the derivative, the minima, the local minima and maxima are never at the origin. The origin always has a positive derivative. The only way a neuron typically would settle or remain around zero is if it consistently introduces error to the system and continues to be suppressed by backpropagation. X times sigmoid, X times logistic. Mm. Now, whoop. Android Studio is updating. Mm. Okay, not compatible with IDE because the IDE contains module com.jitbrains.kmm which conflicts with the plugin. Huh. Plugin. Compose multi-platform for desktop IDE support is not compatible with IDE because the IDE contains module which conflicts with the plugin. They must have built it. Yeah, the plugin must be built into Narwhal now. Yeah. Wow, nice. Okay, so uninstall. This plugin is in maintenance mode. Okay. Compose multi-platform for desktop IDE support plugin is no longer under active. Its functionality is being gradually integrated into the new Kotlin multi-platform plugin, which already includes support for Compose previews on macOS. What this means for you on macOS, we recommend switching to the Kotlin multi-platform plugin, which now includes improved Compose preview support. Oh, nice. Oh, thank goodness. Fucking finally. Plugin versions, June 26. Man, that took long enough. Man, come on. Okay. Compose multi-platform, yeah. Bundled. That was the Kotlin. Hmm. Okay, very cool. Oh no. Oh no. Did they break multi-window support? No. Okay, let's just close Android Studio completely. Jeez. More updates. Update now. Hmm. So far, so good. Okay, let's move Ember to pointy where. Just go. Hmm. Hmm. Okay, Ember. Indeed, because it didn't pop. Let's see what BGDR is. Huh. What was that notification? Column mode. Can't be plugins designed for Kotlin 2 or more. Enable K2. Is K2 not already? Man, why? Hmm. Uh, Enable K2 mode. 2028.3 column will automatically. Uh-huh. Okay. Start now. Okay. Huh. Hmm. Oh my goodness. Interesting. Project environment pre-flight checks. Huh. I guess they took the Flutter Doctor and people like Flutter Doctor, and so they made it interesting. Oh god, I hate all the fucking Flutter bullshit. AI exclude. Great old. Let's see. I'll also exclude the build directories. Let's see. We also want to exclude the Gradle directory. As well as local.properties. Anything secrets. Mm-mm. Oh my god. That's how they're getting around it. Your data will be retained for up to 18 months in certain way where Google cannot tell who provided it. Google cannot fulfill deletion requests during this time. That's how they're getting around it. For our protection. Jesus Christ. Jeez. Hmm. 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 That's interesting. Hmm. Hmm. Focus. Hmm. Oh. See semantics. Okay, good. Window issues fixed now. Hmm. 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 Oh, X, Y, Z. Okay, I'll open it just so I don't forget. Oh, no, let's not open it now. Oh, I've got a lot to catch up on. And if I think about all of it, I'll get overwhelmed. So, one item at a time. Oh man, what is up with this? Oh, that must be part of the new plugin. It's annoying. Projects files? What? Where? Oh, thank goodness. Jeez. Okay. Okay, I got Ember REs. Oh, there we go. Weird. Okay. Let's see. Hmm. 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 Hello again. Input type shape. Okay, did some notes at the meeting to work on the UI a little bit, which I'm gonna hopefully implement tonight. If I do, I'll probably be here late, but yeah, I don't know. Think about it. Um, uh, mm, okay. Okay, reset. I'm gonna yeah, go down and get a little food. And we're gonna read the root mean square layer normalization. Okie doke. Okay. Let's see, reading about root mean square layer normalization. Let's see. And this is layer normalization because I remember reading about yeah, RMS root mean square propagation, uh, which I believe, if I remember correctly, is a form of backprop that normalizes the means and variances uh, as it's going through the backprop. But root mean square layer normalization occurs at the layer level rather than the optimizer level. So it's worth investigating both. Although I remember on the other one, RMS prop loses its benefits when used with RMS layer norms, but I could be misremembering. I'll need to reread that paper. Okay, root mean square layer normalization. Layer normalization. Layer normalization, layer norm, has been successfully applied to various deep neural networks to help stabilize training and boost model convergence because of its capability in handling recentering and rescaling of both inputs and weight matrix. However, the computational overhead introduced by layer norm makes these improvements expensive and significantly slows the underlying network, e.g., recurrent neural networks in particular. In this paper, we hypothesized that recentering invariance in layer norm is dispensable and propose root mean square layer normalization, or RMS norm. RMS norm. Let me change my RMS norm. This is just the abstract. Anyway, it's going to be repeated. RMS norm regularizes the summed inputs to a neuron in one layer according to root mean square, giving the model rescaling invariance property and implicit learning rate adaptation ability. RMS norm is computationally simpler and thus more efficient than layer norm. We also present partial RMS norm, or PRMS norm, where the RMS is estimated from P% of the summed inputs without breaking the above properties. Extensive experiments on several tasks using diverse network architectures show that RMS norm achieves comparable performance against layer norm, but reduces the running time by 7 to 60% on different models. Source code is available at GitHub. Nice. It's awesome. I love it when they have a repo. Introduction, how to train. Actually, let's go ahead and open that up. GitHub. Django. Let's see. BZ Hango. RMS norm. Star. Oh my goodness, wow. What is that, just, it's 6, 7 files? Nice. Simplification of the original layer normalization. Oh, I got a link to this too. Oh, cool. Okay, layer normalization. You know, I don't think I have this paper yet. I might as well download it. So I got, what, 1607? Nope, don't have that yet. And I know I haven't printed it. Let me just go ahead and, yeah, 1608. Got 1608, but not 1607. Okay, cool. Let's go ahead and open that up. And it's only 14 pages. Let's see, what was it? Yeah, I can print that. Boop, 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 boop. Man, I've got to figure out why the A's disappeared when printing. Let's see, downloads to print, 1607, there it is, layer norm. Layer norm. Okay, yep. Okay. And document AI tab downloads to print 607. Put in the AI folder. There we go. Layers. Okay, let's see, layer norm. We got that with RMS. Okay. All right, distractions. Watch. I don't know, 2 years ago. It hasn't moved since 2 years ago. Originally created 6 years ago, but we wrote the formula to use native latex rendering in Markdown. Had problems reading the formula in GitHub dark mode when it was not natively rendered. Oh, very cool. Although it looks like they formatted it wrong. Oh, jeez. Yeah, they have the latex delimiters, but for some reason GitHub's not rendering it. Wonder what happened there. Because if I remember correctly, GitHub's docs for LaTeX don't require you to put it inside of a code block. You can, but you don't have to. What was it? Yeah, because the GitHub Markdown LaTeX. Writing inline expressions. Yeah, it's either single dollars. Let's see, they got single dollars for inline. And then they've got the dollar code block like I prefer. Oh, but they do also have double dollars. Is it because they put spaces? No, that shouldn't be it. Surely wouldn't be that finicky. Surely it would not refuse to render just because they put spaces. Huh, wonder if they've got to know that's not working. Yeah, alternatively, you can use the math code block. Hmm. Yeah, I don't know what that's about. Oh well. I wonder if they use some LaTeX that isn't supported by GitHub, so it just refused to render any of it. Oh well, enough distractions. RMS norm, stored. Okay. Introduction. How to train deep neural networks efficiently is a long-standing challenge. To accelerate, well, I mean, sure, improving dramatically, but okay. To accelerate model converts, Ba et al. Oh no. Oh no, is this paper missing parentheses? No. Did they just not parenthesize that? Oh, yeah. Wow, they just didn't parenthesize it. Did they parenthesize any of their references? Oh, huh. Okay, they just referred to the citation number. Alright. I guess it's okay. But I'll propose the layer normalization layer norm, which stabilizes the training of deep neural networks by regularizing neuron dynamics within one layer via mean and variance statistics. Due to its simplicity and requiring no dependencies among training cases, layer norm has been widely applied to different neural architectures, which enables remarkable success on various tasks ranging from computer vision, speech recognition, to natural language processing. In some cases, layer norm was found to be essential for successfully training a model. Besides, the decoupling from batch-based samples endows layer norm with the superiority over batch normalization and handling variable length sequences using RNNs, recurrent neural networks. Unfortunately, the incorporation of layer norm raises computational overhead. Although this is negligible to small and shallow neural models with few normalization layers, this problem becomes severe when underlying networks grow larger and deeper. As a result, the efficiency gained from faster and more stable training in terms of number of training steps is counterbalanced by an increased computational cost per training step, which diminishes the net efficiency, as shown in Figure 1. One major feature of layer norm that is widely regarded as contributions to the stabilization is its recentering invariance property. The summed inputs after layer norm remain intact when the inputs or weight matrix is shifted by some amount of noise. We argue that this mean normalization does not reduce the variance of hidden states or model gradients, and hypothesize that it has little impact on the success of layer norm. Widely regarded as contributions to the contributing to the stabilization is its recentering invariance property. Widely regarded. We hypothesize that it has little impact on the system. In this paper, we propose root mean square layer normalization, which regularizes the summed inputs to a neuron in one layer with the root mean square statistic alone. RMS norm reduces the amount of computation and increases efficiency over layer norm. Despite the simpler formulation, the RMS normalizer helps stabilize the magnitude of layer activations, ensuring invariance to the rescaling of both weights and datasets. We also show the possibility of estimating RMS on a subset of the summed inputs, maintaining this invariance property. Assuming that the summed inputs have an independent, identically distributed structure. Yep, that's always important. We propose partial RMS norm, where only the first p% summed inputs are utilized for RMS estimation. We thoroughly examine our model on various tasks, including machine translation, image classification, image caption retrieval, and question answering. Experimental results show that across different models, RMS norm yields comparable performance against layer norm, but shows superiority in terms of running speed with a speed up of 7% to 64%. When estimating the RMS norm with partial 6.25% summed inputs, PRMS norm achieves competitive performance compared to RMS norm. 2. Related work. One bottleneck deep neural networks have been hypothesized to suffer from is the internal covariate shift issue, where a layer's input distribution changes as previous layers are updated, which significantly slows the training. One promising direction to solve this problem is normalization. Segedie introduced batch normalization to stabilize activations based on mean and variance statistics estimated from each training mini-batch. Unfortunately, the reliance across training cases deprives batch norm of the capability in handling variable length sequences, though several researchers develop different strategies to enable it in recurrent neural networks. Instead, Salamans and Kingma propose weight normalization, weight norm, to reparameterize weight metrics so as to decouple the length of weight vectors from their directions. Ba et al. Propose layer normalization, which differs from batch norm in that statistics are directly estimated from the same layer without accessing other training cases. Due to its simplicity and effectiveness, layer norm has been successfully applied to various deep neural models and achieves state-of-the-art performance on different tasks. These studies pioneer the research. Let me see. So one batch norm, weight norm. Layer norm. Oh, did it work? Yeah, compared to prior work. These studies pioneer the research direction that integrates normalization as part of the model architecture. This paradigm ensures encouraging performance through shortening model convergence, but at the cost of consuming more time for each running step. To improve efficiency, Arpit et al. Employ a data-independent method to approximately estimate mean and variance statistics, thus avoiding calculating batch statistics. IOF proposed batch renormalization so as to reduce the dependence of many batches in batch norm. Ulyanov et al. Replace batch normalization with instance normalization for image generation. Hoffer et al. And Wu et al. Observe that L1 norm can act as an alternative of variance in batch norm with the benefit of fewer nonlinear operations and higher computational efficiency. Okay, that's related to what I wanted to try. Hoffer et al. And Wu et al. Observe that L1 norm can act as an alternative of variance in batch norm with the benefit of fewer nonlinear operations and higher computational efficiency. Nevertheless, all these work still follow the original normalization structure and utilize mean statistic estimated from the whole summed inputs to handle recentering and variance. Different from these related work, the proposed RMS norm modifies the normalization structure by removing the recentering operation and regularizing the summed inputs with RMS alone. Our model only maintains the rescaling invariance property, which we find can be inherited when the RMS is estimated from only a subset of the summed inputs, partially inspired by the group normalization. As a side effect, our model reduces the computational overhead and increases efficiency. Recently, Zhang et al. Show that with careful initialization, residual networks can be trained as stable as those with normalization. However, the approach mainly aims at improving residual networks and cannot be freely switched without modifying all initialization layers. Besides, it is not trivial to be adapted to other general neural networks, such as recurrent neural networks, where model depth expands along the variable sequence length. By contrast, our model is simple, effective, and can be used as a drop-in replacement of layer norm. Background. We briefly review layer norm in the section based on the standard feed-forward neural network. Given an input vector x member of R to M, a feed-forward network projects it onto an output vector y member of R to the N. Nancy, through a linear transformation followed by a nonlinear activation as follows. Activation of I is equal to J summing over set 1 to M of the weight ij times xj, where yi equals f of ai plus bi. Oh, that's an interesting way to formulate it instead of the whatever. Where wi is weight vector to the ith output neuron, b is biscalar, which is usually initialized by 0, and f function is an element-wise nonlinear function. A member of R to the n denotes the weight summed inputs to neurons, which is also the target of normalization. This vanilla network might suffer from internal covariate shift issue, where a layer's input distribution changes as previous layers are updated. This could negatively affect the stability of parameters gradients, delaying model convergence. This is always an important issue, internal covariate shift. This could negatively affect the stability of parameters gradients, delaying model convergence. To reduce this shift, layer norm normalizes the summed inputs so as to fix their mean invariance as follows. It's interesting. Yes, the activation equals activation minus the mean all over the variance times g of I. Yi same. Oh, but is the equal yi is equal to f of the mean of I, or the normalized a plus the bias, where a hat, no, that's not hat, is the ith value of a vector a member of R to n, which acts as the normalized alternative of ai for layer activation. G member of Rn is the gain parameter used to rescale the standardized summed inputs and is set to 1 at the beginning. Oh, so it's a learnable parameter. Mu and sigma squared variance are the mean and variance statistic respectively estimated from raw summed inputs at A. So the mean, the average over the activations. And then the variance, or the standard deviation rather, is the square root of the average of the activation minus the mean squared, and then sum all of that and divide by n, so the average of this. So yeah, I mean that's the standard deviation formula. So yeah, mean standard deviation. But we shouldn't need to calculate the actual square root because the formula uses the variance. So we're going to be squaring that anyway, but whatever. RMS norm, a well-known explanation of the success of layer norm is its recentering and rescaling invariance property. The former enables the model to be insensitive to shift noises on both inputs and weights, and the latter keeps the output representations intact when both inputs and weights are randomly scaled. In this paper, we hypothesize that the rescaling invariance is the reason for success of layer norm rather than recentering invariance. We propose RMS norm, which only focuses on rescaling invariance and regularizes the summed inputs simply according to the root mean square statistic. Intuitively, RMS norm simplifies layer norm by totally removing the mean statistic in equation 3, at the cost of sacrificing the invariance that mean normalization affords. When the mean of summed inputs is 0, RMS norm is exactly equal to layer norm. Although RMS norm does not recenter the summed inputs as in layer norm, we demonstrate through experiments that this property is not fundamental to the success of layer norm, in that RMS norm is similarly or more effective. RMS measures the quadratic mean of inputs, which is RMS norm forces the summed inputs into a square root of n scaled unit sphere. By doing so, the output distribution remains regardless of the scaling of input and weight distributions, benefiting the stability of layer activations. Although Euclidean norm, which only differs from RMS by a factor of square root of n, has been successfully explored, we empirically find that it does not work for layer normalization. We hypothesize that scaling the sphere with the size of the input vector is important because it makes the normalization more robust across vectors of different size. As far as we know, the idea of employing RMS for neural network normalization has not been investigated before. Invariance analysis. Invariance measures whether model output after normalization changes highly in accordance with its input and weight matrix. Ba et al. Show that different normalization methods reveal different invariance properties, which contributes considerably to the model's robustness. In this section, we theoretically examine the invariance properties of RMS norm. We consider the following general form of RMS norm: y equals f of the weights times x over the root mean squared of A of activations, Hadamard product multiplied by g, the scaling factor, plus b, where circle dot denotes element-wise multiplication. Our main results are summarized in Table 1. RMS norm is invariant to both weight matrix and input rescaling because of the following linearity property of RMS. Our root mean squared of alpha times x equals alpha times RMS of x, where a is a scale value. Suppose the weight matrix is scaled by a factor of del, i.e. w prime equals del w, then this change does not affect the final layer output. Because y prime equal to f of, same thing, but weight prime times x over RMS of activation prime. Hadamard product of g plus b is identically equal to a function of, I suppose that's supposed to be derivative, w prime equals del w. Okay, so using partial derivative w of x with respect to the root mean squared of a times g plus b equals y. By contrast, if the scaling is only performed on individual weight vectors, this property does not hold anymore, as different scaling factors break the linearity property of RMS. Similarly, if we enforce a scale on the input with a factor of del, i.e. x prime equals del x, the output of RMS norm remains through an analysis analogous to that in equation 7. We can easily extend the equality to batch-based inputs as well as the whole dataset. Therefore, RMS norm is invariant to the scaling of its inputs. The main difference to layered norm is that RMS norm is not recentered and thus does not show similar linearity property for variable shifting. It is not invariant to all recentering operations. Okay, gradient analysis. The above analysis only considers the effect of scaling inputs in the weight matrix on the layer output. In general setting, however, a RMS norm enhanced neural network is trained via standard stochastic gradient descent approach, where the robustness of model gradient is very crucial to parameters update and model convergence. See also Santakar et al., who argue that the success of normalization methods does not come from the added stability to layer inputs, but due to increased smoothness of the optimization landscape. Okay, isn't the optimization landscape smoother because of the stability to layer inputs? I'm gonna just assume they know better than I do. But, God, I'd like to see that paper and see the argument. General setting, however, RMS norm enhanced neural network is trained via standard stochastic gradient approach, where the robustness of model gradient is very crucial to parameters updated and model convergence. Who argue that the success of normalization methods does not come from that stability, but to. In this section, we investigate the properties of model gradients RMS norm. Give me a loss function L. We perform backpropagation through equation 4 to obtain the gradient with respect to parameters g, b as follows. Del L over del B equals del L over del V. So the partial derivative layer with respect to B, the bias is equal to the partial derivative layer with respect, or loss function with respect to V, blah, 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 blah. Okay. And the derivative of the loss with respect to G is equal to the derivative of loss with respect to V, Hadamard product Wx over the root mean squared of A. Where V is short for the whole expression inside F in equation 4, and del L over del V is the gradient back propagated from L to V. Both gradients del L over del B and del L over del G are invariant to the scaling of inputs X and the weight matrix W in the case of del L over del G because of the linearity property in equation 6. Besides, the gradient of G is proportional to the non-linearized, gradient of G is proportional to the normalized summed inputs rather than raw inputs. Jeez. This powers the stability of the magnitude of G. Unlike these vector parameters, oh yeah, because it's del L with respect to G, so yeah, it's a learnable parameter. Besides, the gradient of G is proportional to the normalized summed inputs rather than raw inputs. This powers the stability of the magnitude of G. Unlike these vector parameters, the gradient of the weight matrix W is more complicated due to the quadratic computation in RMS. Formally, oh my goodness, del L over W. There's the partial derivative of loss with respect to the weights is equal to the sum over n of the input X transpose cross with the diagonal of G multiplied by the partial derivative of loss with respect to V, all cross with R, where R is equal to is that outer product? Oh, yeah. Okay, they actually clarified, thank goodness. Where R equals 1 over R minus A times I minus WX times WX transpose all over in R minus A squared. Ugh. Diag dot denotes the diagonal matrix of input. Circle X, circle cross denotes the Kronecker product, and I indicates identity matrix. Okay. For clarity, we explicitly use X to represent matrix multiplication. Matrix term R associates gradient of W with both inputs X and weight matrix W. With a thorough analysis, we can demonstrate that this term is negatively correlated with both input and weight matrix scaling. After assigning a scale of del to either input X times X prime equals del X or weight matrix W prime equals del W, we have R prime equals, 1 over del RMS times A. All times I minus del WX times del WX transpose all over n times del squared RMS. Oh, well, del squared, so the second partial derivative of root mean squared equals 1 over del R. We put the scaled term R back into equation 9. We can easily prove that the gradient del L, partial derivative of loss with respect to weights, is invariant to input scaling, but keeps the negative correlation with weight matrix scaling. Reducing the sensitivity of gradient, partial derivative, the gradient, the loss with respect to weights, to the scaling of inputs ensures its smoothness and improves the stability of learning. On the other hand, the negative correlation acts as an implicit learning rate adapter and dynamically controls the norm of gradients, which avoids large norm weight matrix and improves model convergence. 5. PRMS norm. The rescaling invariance property of RMS norm ascribes the linearity property of RMS. Considering that neurons in one layer often have independent, identically distributed structure, we argue that RMS can be estimated on a subset of these neurons rather than all of them. We propose partial RMS norm, PRMS norm. Given the unnormalized input A, PRMS norm infers the RMS statistic from first 8% elements of A, RMS A equals K equal to a ceiling of n times P. Notes the number of elements used for RMS estimation. So it's the ceiling round up. The linearity property still holds for RMS as in equation 6, which indicates PRMS norm shares the same invariance properties as RMS norm as shown in table 1. RMS is a biased estimation of the RMS, which is often inaccurate. Though theoretically PRMS norm approximates to RMS norm, we observe gradient instability where the gradient tends to explode with small m. In practice, however, models with PRMS norm can succeed in satisfactory convergence with a partial ratio of 6.25. Oh, so that's where they're getting the speed up from. What was it they said? But reduces running time from 7 to 64% on different models. Is that because they're able to take the partial norm, so they're not actually... Oh, no, okay. Several times using the... So that RMS norm is comparable. We're just running by seven. Okay, so that's RMS norm. They did not claim that for PRMS norm. Okay. So it's not just because they're sampling a subset. Experiments. To test efficiency of layer normalization across different implementations, we perform experiments with TensorFlow, PyTorch, and Theano. We add RMS norm to different models, comparing against an unnormalized baseline in the layer norm. These models are based on diverse architectures covering different RNN variants, convolutional and self-attention models, and various activations such as sigmoid, tanh, and softmax, with initialization ranging from uniform, normal, orthogonal with different initialization ranges or variances. Unless otherwise noted, all speed-related statistics are measured on 1 titan Pascal. Reported time is averaged over 3 runs. We also list the standard deviation of these 3 runs. Machine translation. Machine translation aims at transforming... Oh, let me look at this figure 2 first. Sacre bleu. Okay. Machine translation. Machine translation aims at transforming a sentence from one source language to another target language. We focus on neural machine translation based on attention-enhanced encoder-decoder framework. We train 2 different models, a GRU-based RNN search, recurrent neural network search, and a self-attention-based neural transformer. On WMT 14 English-German translation task, more details about the experimental settings as well as comparison with weight norm are listed in Appendix A1. We first experiment with RNN search. Normalization is added to the recurrent connections in feed-forward layers. Apart from RNN search without any normalization baseline, and with layer norm, we also compare against the same model equipped with L2 norm, i.e. replacing RMS with L2 norm, which has been observed to improve lexical selection. Figure 2 illustrates the evolution of BLEU score on our development set after every 30K training steps, and Table 2 summarizes the test results. In short, both layer norm and RMS norm outperformed the baseline by accelerating model convergence. They reduced the number of training steps until convergence by about 50% and improved test accuracy. With RMS norm being comparable to layer norm, this supports our hypothesis that rescaling invariance is the core property of layer norm, and that RMS norm is an effective substitute. 30K training steps in Table 2 summarizes test results. Where both layer norm and RMS norm outperformed the baseline by accelerating model convergence. They reduced the number of training steps until converged by about 50% and improved test accuracy, with RMS norm being comparable to layer norm. Supports our hypothesis that rescaling invariance is the core property of layer norm. RMS norm. Our results with L2 norm show that it fails to improve the model. Results in Table 2 highlight the challenge that RNN with layer norm and TensorFlow suffers from serious computational inefficiency, where layer norm is slower than the baseline by about 67%. In this respect, RMS norm performs significantly better, improving upon layer norm by 25%. Results with L2 norm show that it fails to improve the model. But L2 norm has been observed to improve lexical selection. Results in Table 2 highlight the challenge that RNN with layer norm and TensorFlow suffers from serious computational inefficiency, where layer norm is slower within the baseline by about 67%. In this respect, RMS norm significantly better, improved upon layer norm by 25%. Table 3 further lists translation results of different models implemented in Theano and PyTorch. Overall, RMS norm yields comparable translation quality compared with layer norm, but incurs less computational overhead, outperforming layer norm with speedups ranging from 11% to 34%. In addition, we observe that though in theory the amount of computation in PRMS norm is less than that in RMS norm, PRMS norm p equals 6.25 sometimes tends to be slower. We ascribe this to the non-optimal implementation of tensor slicing operation in these computational frameworks, which can be improved with specific low-level coding. In PRMS norm, the partial ratio p directly controls the accuracy of estimated RMS, therefore affecting the stability of model training. Figure 7 shows the effect of P on model performance. Surprisingly, we find that the scale of P has little influence on the final translation quality in RNN search. Using a small ratio does not significantly degenerate BLU score. We set P to 6.25% for all following experiments. We also experiment with transformer, which is based on self-attention, avoiding recurrent connections and allowing the higher degree of parallelization. Still, layer normalization is an important part of the architecture. We use an in-house TensorFlow implementation of the transformer and employ the base setting as in 31 with all models trained for 300K steps. We treat transformer with no normalization as our baseline and compare RMS norm enhanced transformer with layer norm equipped transformer. Table 4 shows the results from which we observe the importance of normalization for transformer, without which training fails. RMS norm achieves BLU blue scores comparable to layer norm and yields a speedup of 7% to 9%. Compared with recurrent neural network search, relative cost of normalization is lower because there are significantly fewer sequential normalization operations in transformer. Effect of normalization on mean and standard deviation. Table 5 shows the distribution of mean and standard deviation of hidden representations across token positions for an RNN search model. Mean and standard deviation are unstable in the baseline and observed by Ba et al. Due to their normalization properties, both RMS norm and layer norm stabilize standard deviation. Although the mean in RMS norm is not normalized, in practice it is more stable than the mean of the baseline. This supports our hypothesis that RMS norm stabilizes recurrent activations without the need to explicitly normalize the mean. I mean, we have bias. We have bias. I mean, yeah, I feel like it's, unless I'm missing something, it's kind of intuitive or obvious that, I mean, if you're adding biases and the bias parameters are still learnable parameters, then rather than adjusting the mean, I mean, if you did rescale the mean to 0 and it needed to deviate from 0, then that's what the bias parameters would do. Else I'm forgetting. Oh, I forget. Does it normalize the activations? Wait, oh, does it? I forget. It normalizes the activations from the previous layer, but then we'll still do the computation adding the bias for the pre-activation. It still adds bias to the pre-activation for the current layer based on the output activation to the previous layer, and it's normalizing the output, right? Right. Yeah. So norm stabilizes hypothesis that norm stabilizes recurrent activations without the need to explicitly normalize the mean. On the robustness of RMS norm. One remaining question is whether the recentering operation in layer norm, which RMS norm abandons, makes models more robust towards arbitrary weight bias initializations. Yeah, that's. We perform an experiment on RNN search with Nematis in TensorFlow and change the center of weight initialization to 0.2. Results in figure 4 show that layer norm becomes very unstable with abnormal initialization, but RMS norm is more robust. Both underperform the original initialization. Our empirical evidence so far suggests that RMS norm is similarly robust as layer norm or more. Sacre bleu, score curve of layer norm and RMS norm on news test 2013. Dev set when the initialization center is 0.2. 6.2 Convolutional neural network daily mail reading comprehension. This reading comprehension task is a closed style question answering task where models are required to answer a question regarding to a passage, and the answer is anonymized entity from the passage. We train a bidirectional attentive reader model proposed by Herman et al. On the CNN corpus. More details about the experimental settings are given in Appendix A.2. We compare RMS norm with both layer norm and batch norm. Figure 5 and Table 6 show the results after normalizing RNN by batch norm with separate statistics for each time step in the sequence. Both batch norm LSTM and batch norm everywhere help speed up the convergence of training process. By contrast, layer norm and RMS norm not only converge faster than batch norm, but also reach lower validation error rate, though PRMS norm performs slightly worse than RMS norm. Although in Figure 5, the performance of RMS norm and layer norm is comparable, RMS norm is around 50% faster than layer norm, as shown in Table 6. 3. All right, now validation set for the tentative reader model. Valid error rate. Baseline. Wow, those are all much faster. We got the baseline, we got batch norm everywhere. We got batch norm, LSTM, long, short-term memory. We got layer norm, RMS norm, PRMS norm. Image caption retrieval. Image caption retrieval is a cross-modal task aiming at learning a joint embedding space of images and sentences, which consists of two subtasks, image retrieval and caption retrieval. The former ranks a set of images according to a query caption, and the latter ranks a set of captions based on a query image. We train an order embedding model, OE, proposed by Van Drove et al., on the Microsoft COC dataset using their public source code in Theano. Model details about experimental settings are provided in Appendix A3. We compare RMS norm with two models, one without any normalization baseline and one with layer norm. Figure 6 shows the R at K curve on validation set after every 300 training steps, and Table 7 lists the final test results. Across all these metrics, RMS norm and layer norm consistently outperform the baseline in terms of model convergence as shown in Figure 6. We observe that on the validation set, RMS norm slightly exceeds layer norm with respect to recall value. For the final test results as shown in Table 7, both RMS norm and layer norm improve the model performance, reaching higher recall values except layer norm on R at 5 and lower mean rank, though RMS norm reveals better generalization than layer norm. Besides, results in Table 8 show that RMS norm accelerates training speed by 40% to 64% compared with layer norm, highlighting better efficiency of PRMS norm. CIFAR-10 classification. CIFAR-10 is a supervised image classification task with 10 different classes. We train a modified version of ConvPool CNNC architecture and follow the same experimental protocol as Salamans and Kigma. Batch norm, layer norm, and weight norm are included for comparison. Training details are given in Appendix A4. Figure 9 and Table 10 show the results. Models enhanced with the normalization technique converge faster than baseline, among which batch norm performs the best. Similar to previous observation, we also find that layer normalization works worse than batch norm and weight norm for image processing, though layer norm outperforms baseline by shortening model convergence, it fails to generalize the test set, degenerating the test error by 1.53%. In contrast, RMS norm shows better generalization, surpassing the baseline by 0.013% and saving about 20.5% training time compared to layer norm. PRMS norm gains further speed up of 2.6%, albeit at the cost of sacrificing test accuracy of 1.54%. Conclusion and future work. This paper presents RMS norm, a novel normalization approach that normalizes the summed inputs according to the RMS. RMS norm preserves the rescaling invariance property of layer norm, but eschews the recentering invariance property, which contributes less to the model training. Compared with layer norm models, RMS norm suffers from less computational overhead. RMS norm can be easily applied to different model architectures as drop-in replacement of layer norm. Experiments on several NLP tasks show that RMS norm is comparable to layer norm in quality, but accelerates the running speed. Actual speed improvements depend on the framework, hardware, neural network architecture, and relative computational cost of other components, and we empirically observe speedups of 7% to 64% across different models and implementations. Our efficiency improvement come from simplifying the computation, and we thus expect them to be orthogonal to other means of increasing training speed, such as low precision arithmetic and GPU kernel fusion. We also experimented with PRMS norm, which estimates the RMS on a subset of the summed inputs. While theoretically faster, we did not consistently observe empirical speed improvements for PRMS norm. We leave it to future work to investigate if the performance can be improved via code optimization. In the future, we would like to take more analysis about the success behind RMS norm. Inspired by recent success of L1 norm for batch norm, we will explore different norms for RMS norm and simplify other normalization techniques such as batch norm. Acknowledgements. We thank the reviewers for their insightful comments and Antonio Valerio Marcelo Barone for support with weight normalization for MT. Project has received funding from the grant by the European Union. Bao Zhang also acknowledges the support of the Baidu Scholarship. This work has been performed using resources provided by the Cambridge Tier 2 system operated by the University of Cambridge Research Computing Service, funded by EPSRC Tier 2 capital grant. References, appendices. Wow. Oh, wow. Times 30K. Wow. Wow, wow, wow. Wow. Yeah, that does converge a lot faster. That's insane. Baseline and weight norm. Baseline and weight norm are pretty much the same. Okay. So that's RMS norm. Which, yeah, I was planning on implementing, but it's past midnight now. Ugh. Go away. Bad chatter. Bad. Ban. Bye-bye. Somebody's selling their Twitch account. Can I flag? Oh well. Okey-doke. I'll be right back. I'm gonna go get that layer norm paper. Okay. Okay, so let's see. It's the okay, so they don't believe the mean rescaling or shifting the mean, adjusting the mean has, or they don't think that's important, which makes sense because we have bias parameters that can effectively do the same thing if we did shift the mean. It's mainly the rescaling invariance that gives it the stability and the smoothness of the error surface or the optimization surface. And they did mention that there's previous work using the L1 norm. There's Hoffer et al., Wu et al. Observed that L1 norm can act as an alternative variance in batch norm. Let's see, batch norm. No. It was it weight norm. Yeah, batch norm is the one that performs well in general, and weight norm was the one that underperformed. Yeah, that one's using weight norm. Oh, let's see, 10 and 33, I think. Yeah. Norm matters. Efficient and accurate normalization schemes and deep networks. 10 and 33. L1 norm, batch normalization for efficient training of deep neural networks. L1 norm batch normalization. Yeah, because that's basically the same idea I had. Based on weight decay, doing the opposite of weight. Oh, that's right though. I'm not thinking about normalizing. Yeah, that's right. Okay, so we'll have to. Yeah, that's right. That's right. Because they're normalizing the activation, the distribution of the activations, which is post weights. Yeah, so layer norm. Yeah, deep neural networks trained with some version of stochastic gradient substantially outperform previous approaches of various supervised learning tasks of computer speech processing, but state of the art, deep neural networks are required many days of training. It's possible to speed up learning by computer gradients for different subsets of training cases on different machines or splitting the neural network itself over many machines. But this can require a lot of communication complex effort. It also tends to lead to rapidly diminishing returns as the degree of parallelization increases. An orthogonal approach is to modify the computations performed in the forepass the neural net to make the learning easier. Recently, batch normalization has been proposed to reduce training time by including additional normalization stages in deep neural networks. The normalization standardizes each summed input using its mean and standard deviation across the training data. Feed-forward neural networks trained using batch normalization converge faster, even with simple gradient descent, or simple stochastic gradient descent. In addition to training time improvement, the stochasticity in the batch statistics serves as a regularizer during training. Despite its simplicity, batch normalization requires running averages of the summed input statistics. And feed-forward networks with fixed depth, it is straightforward to store the statistics separately for each hidden layer. However, the summed inputs to the recurrent neurons in a recurrent neural network often vary with the length the sequence, so applying batch normalization to recurrent neural networks appears to require different statistics for different time steps. Furthermore, batch normalization use a compact recurrent neural networks to self-sequence. Furthermore, batch normalization cannot be applied to online learning tasks or to extremely large distributed models where the many batches have to be small. This paper introduces layer normalization, a simple normalization method to improve the training speed for various neural network models. Unlike batch normalization, the proposed method directly estimates the normalization statistics from the summed inputs to the neurons within a hidden layer. So the normalization does not introduce any new dependencies between training cases. We show that layer normalization works well for recurrent neural networks, improves both the training time and the generalization performance of several existing recurrent neural network models. Background. A feed-forward neural network is a nonlinear mapping from an input pattern X to an output vector Y. Consider the Lth hidden layer in a deep feed-forward neural network and let AL be the vector representation of summed inputs to the neurons in that layer. Summed inputs are computed through a linear projection with a weight matrix WL and the bottom-up inputs HL given as follows. I'm getting way too deep into this. But the point is, it's normed over the activations. Yeah, which I feel like. Hmm. 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 Oh, I'll save this one for tomorrow. I should not have drank so much coffee. Okay, yeah. Hmm. Mm-hmm. Yeah. Still adding the bias out external to. Hmm. Hmm. Yeah, that's ugly. Hmm. 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 Okay. Uh. Okay. So what? Let's see. They did not compare. That's right. They did not compare. They mentioned the L1 norm. They did not test L1 norm. Let's see. They did mention batch norm. They mentioned batch norm, but they don't have any test or any data for it. Hmm. Mm. The contrast layer norm and RMS norm not only converge faster than batch norm, but also reach lower validation error rate. So PRMS norm performs slightly worse than RMS norm. Okay, here we go. There's the batch norm data. Batch norm everywhere. Batch norm LSTM. Yeah. Hmm. It's interesting. Hmm. Hmm. Inspired by recent success of L1 norm, for batch norm, we will explore different norms for RMS norm, simplify other normalization techniques such as batch norm. Future. Hmm. Okay. Let's see. Hmm. Hmm. Yeah, I'll have to make sure that the math works out, but I still want to try it. Okay, we'll read this one tomorrow. Layer normalization. Okay, this is. I want to implement it. I'll do that after layer normalization since layer normalization is the prior work. Hmm. Okay, yeah, I guess that's it. Bye, Twitch.